In this video, we will be reviewing linear algebraic equations, eigenvalues, and eigenvectors. This is a very important concept that we can make use in linear algebra for diagonalization, and in differential equations, we can solve multiple differential equations at once using these properties. So, in order to find eigenvalues and eigenvectors, we need to follow these four steps. First, our theory is that A times eigenvector V equals to lambda, which is the eigenvalue, times V. And we can make use of this to confirm our eigenvalue or eigenvectors. However, it is not that necessary since these four steps will ultimately help you find the eigenvalue and the vectors. Important note is that when we start by setting determinant a minus lambda I equal to 0, you might not know what I is. So basically, I is called the identity matrix, and it has to be a square matrix. So I is a square matrix, okay? And depending on the size of A, okay, for example, let's say A is a 2 by 2 matrix, our identity matrix will be a 2 by 2 matrix, and it will look just like this. Okay, so only this diagonal, okay, from top left corner to bottom right corner, you will have ones, and the other entries will be zero. So, for example, for a 3 by 3 identity matrix, you will have something like this, where you have 1 0 0 0 1 0 and 0 0 1 for this identity matrix in R3. So this is how we use it. So when we start by setting the determinant of a minus lambda I equal to 0. And then we're going to solve for the eigenvalues, okay? Eigenvalue is the lambda symbol. So if you have a 2 by 2 matrix, you're likely to have two eigenvalues, or if you have 3 by 3, you will have three eigenvalues. Obviously, repetition exists, and in those cases, it does affect the eigenvectors, but it doesn't really matter because in differential equations, in ordinary differential equations, we are covering 2 by 2 matrices. So you all need to just focus on 2 by 2 unless you're taking linear algebra. Now, for step 3, we will plug it back into a minus lambda I. So we're not going to go with the determinant route. We're going to go back into the matrix. We're going to have the matrix A, and we're going to subtract lambda I, where lambda is a coefficient, guys. So when you multiply lambda with an I, you're going to get a matrix, and you're going to make a subtraction between these two matrices to get another matrix. And that matrix is going to be a very useful matrix where we have variables, and those variables will help us get our eigenvectors. And then obviously you have your eigenvectors and eigenvalues, so at that point you know what to do. After that, for differential equations, depending on what kind of eigenvalues and vectors we have, we will have different kinds of solution sets. We will focus on real solutions and complex solutions with eigenvalues, and those will be very useful in the future. Now let's use what we learned to solve this matrix to find the eigenvalues and the eigenvectors of this matrix. Well, we need to start with a minus lambda I. So a is this matrix, so we will subtract a minus lambda I. Well, you might ask, hey, we don't know lambda. What is lambda? So you're just going to say 3 minus lambda. You can leave it unknown. That's completely okay. So we will have -1 minus lambda, and this will be our new matrix, okay? And now we want to find the determinant of this, and then we're going to set that equal to 0. Remember, guys, what we did was set the determinant of a minus lambda I equal to 0, okay? That's the important part. So how do we find the determinant? You basically cross multiply these two guys, okay? And you will have 3 minus lambda multiplied with -1 minus lambda, and then minus and multiply these two, you will have -8 here. So you will have 3 minus lambda multiply with -1 minus lambda plus 8, and set that equal to 0. That's it, guys. After this point, all you have to do is to find the eigenvalues. So you will have negative 3. I'm just going to distribute this 3 minus 3 lambda plus lambda squared plus 8 equal to 0. Therefore, our final equation will be lambda squared minus 2 lambda plus 5 equal to 0. All right, now this is a quadratic equation, and what we want to do is to find lambda. Well, I can see that this is going to be giving us complex roots. So I want to start with the b squared minus 4ac method, and then do negative b minus square root of b squared minus 4ac divided by 2a. So that will give us b squared is 4 minus 4 times 1 times 5. So our delta will be 4i in this case. So our roots will be negative b, which is 2, plus or minus delta, which is 4i, divided by 2a, and a is 1. So our solutions for eigenvalues are 1 plus 2i. I'm going to call this eigenvalue 1, and 1 minus 2i, and this will be lambda 2, okay? Lambda 2. Now that we have these lambda values, we have our eigenvalues. We finished first part of the problem. The second problem is, what are our eigenvectors? Well, guys, we need to go back to our original matrix, okay? Go back all the way to the top, all the way where you had A, okay? Copy this, okay? In your exam, just know what your matrix gives you, okay? And then take it down here, take it all the way here, okay? Now that we have our A, go ahead and subtract A minus lambda I, okay? Do that. So we will have 3 minus, let's do lambda 1 here, 1 plus 2i, okay? And then since I is a diagonal matrix, we have the diagonal, so we will subtract that from the last entry as well. So we will have exactly this matrix here, okay? And if we go ahead and further simplify our equation, our matrix will be 2 minus 2i, negative 2, 4, negative 1, I'm sorry, negative 2 minus 2i. Okay? At this point, there are many ways you can find the eigenvectors. If you have taken linear algebra, you might know to do the row reduction. But we're not going to do that. The very simple method is for these cases is that treat this as a variable x1, and this will be x2, okay? And this will ultimately be equal to 0. We know that that's equal to 0. So we're gonna say that 2 minus 2i x1 plus, okay, negative 2. I'm taking this first equation from the first row, x2 equal to 0. Okay, this is a very important step. So 2 minus 2i x1 equals to 2x2. Well, let's solve x2 in terms of x1. So 1 minus I x1 equals to x2. Okay, this is a very important step, guys. So now that we have one really simple solution, one variable in terms of the other, okay, we basically call these variables basic variables because we can express this variable with a multiple of the other variable, and since we don't have any information on x1, that will be a free variable. So you're gonna take your free variable, okay, let's call this x1, or rather 1, okay? So you're gonna have like x1 constant here, and 1 x1, okay, your variable x1 is x1, we don't have any information about that, but x2 is 1 minus I, okay? So you have this is basically giving you a brief description about your variables. You have x1 as your variable, and your second variable is something like 1 minus I x1, which is what we call x2, okay? So this ultimately, this vector is your v1 vector, okay? v1. So I'm just going to write that down here. v1 is 1 minus I. And remember guys, from the first equations, we are able to express v1 in terms of cv1, okay? Like any constant multiplied with v1 will also be okay. If you have 5 over like 5 minus, I don't know, 5i, this is also okay because it's the important thing is the vector, guys. It's not the constants, okay? So obviously the ratio is important due to it's being a like, I mean, technically, yeah, it is important, the ratio, like the ratio of the first and the second entry. However, when you multiply the entire vector with a constant, it doesn't really matter. So you might get little different results what from what you expect. You might get a negative version of this or something else from a different method, but that's also okay because it's the same thing mathematically. Now we're gonna do the same thing and get our second eigenvector. So what we did, guys, was we did this vector, this matrix minus v1. Now we're gonna get that matrix minus v2. Okay, so v2, I'm sorry, lambda 2. I should say lambda 2. What was lambda 2? Lambda 2 was 1 minus 2i. Okay, you go ahead and write that down, 1 minus 2i. Then write your matrix here again. So our matrix was just like this. Now we're gonna say a minus lambda 2. So we're gonna have 3 minus 1 minus 2i, negative 2, 4, and negative 1 minus 1 minus 2i. Okay, and this is our matrix. This is our new matrix. So we're gonna go ahead and make the simplification. So we're gonna now when we simplify, we will have 2 plus 2i, negative 2, 4, and negative 2 plus 2i. Well, now you can pick either of the rows, the first row or the second row. They both must result in the same eigenvector. And in the previous one also, you could pick the second row as well. That shouldn't affect your answer unless you made a mistake along the way. So let's go ahead and find our second eigenvector. So this will be our constant for x1 minus x2 equals to 0. And then 2x2 will be equal to 2 plus 2i multiply with x1. So x2 will be equal to 1 plus I times x1. Okay, now that we have x2 in terms of x1, our free variable is x1, and our x2 will be 1 plus I in terms of x1. So if you multiply this with x1, you will get this vector. So this vector is our second eigenvector. So our first eigenvector was eigenvector 1. Eigenvector 1 was 1 over 1 minus I believe. And we have our eigenvalues as well. So that's how you solve the solutions. I'm just trying to look for the, yeah, here we go. V1 is 1 over 1, and for the second entry, we have 1 minus I. And our eigenvalues were 1 plus 2I and 1 minus 2I. And this is how you should solve eigenvalue and vector problems.